So today we will continue discussing about VSATs. Okay. So in the last class we had seen the structure, okay, which is the satellites, and then they're communicating to your outdoor units, and then to indoor units, and then to the user terminals, right? So here also you can see your satellite, and then your hub equipment, and then host computer. So between each of these, you will always have sending of information and receiving of information. Okay, right. So this is the basic structure for VSAT and broadcasting. Okay, one information here, one thing that happens here is whatever information is there, it gets broadcasted with the help of the either it could be outdoor unit or it could be hub equipment. Okay, access the other way from VSATs to hub is more complicated. So if you want to access information from the VSAT to the hub, okay, which is the reverse process, okay, from the VSAT to the hub is a little complex process, okay, but then sending and receiving information from the satellite is easy. The most popular access method is FDMA. Okay, so divisions are done based on the frequency lines, which allows the use of comparatively low power VSAT terminals. TDMA is not efficient because we will be having a lot of time delays. So if I allocate certain time slots, then that wouldn't be appropriate, because by the time the signal passes from one end to the other, okay, there is a lot of delay that happens. So those time slots allocated will be nullified or it would go waste. So the best possible way to do it is using your FDMA. So the other reason is that TDMA is not efficient for low density uplink traffic from VSAT. Okay, so if there is not much of data available for sending information, then TDMA doesn't become that proper format. The traffic in VSAT network is mostly data transfer of a bursting nature. Okay, so it can be sometimes a lot of information at one point of time, or sometimes there couldn't be any information at all, just minute, just very few bits of data can be transferred from one end to the other. So the examples are being inventory control, credit verification, reservation requests. Okay, so which means this doesn't happen all the time, just for some time this will happen, and then once it gets the verification, then immediately the signal gets back and sends an acknowledgement stating that it can proceed to the next level. So these are all with regards to payment. Okay, if in case you're reserving your tickets, if in case you're going ahead with the payment, so that is when all this comes into picture. So allocation of time slots in TDMA mode can lead to low channel occupancy. So since the channels are not occupied much, and it will lead for low channel occupancy, which means utilization of bandwidth doesn't happen properly. So we go ahead and use the technique called FDMA. And a form of DAMA. Okay, so it's also referred to as demand assigned multiple access. So whenever there is a demand, then it is request, just like your SAS, software as a service. Okay, this is a very much a well-known term when you think of cloud computing. You do not use the service every time, but whenever you need, the service is requested, and then you utilize, you make use of the service, and then you give it away once you're done with your computations. So say for example, you want to compute some huge calculation and you need a better configuration computer or a server. So you can opt it for some time, and then you can pay for the time that you have utilized it for. And then once it's done, you can release it to its service provider. So you are taking things for higher. Okay, so it can be servers, it can be storage, or whatever for that matter, is employed in some systems in which channel capacity is assigned in response to the fluctuating demands of VSATs in the network. Okay. So based on the demand, you try to take services. As pointed out in 1990 by Abramson, the problem of access then shifts to how users may access the reserve channel in an efficient way. So that is our challenge, right? To utilize the channel in a more efficient way. If we cannot utilize it, then it's going to be a wastage of resource, right? So in order to make the best use of the resources available, we go ahead with the FDMA technique. Then not only that, he presented a method of CDMA using spread spectrum techniques, which is coupled with Aloha protocol. Okay. So what is this Aloha protocol? It's a random access method in which packets are transmitted at random in defined time slots. So all the informations are actually converted into packets, and these packets are thrown in random based on uh, the time slots. Okay, it's an interesting algorithm actually, where you can look into it. Okay. Fine. The system is used where the packet time is small compared with the slot time, and provision is made for dealing with packet collisions. So if in case there is a collision of packet, then there can be a loss of data. So we should make sure that at different time slots these packets are arriving. So the source and destination should be in sync while transmitting this information, which can occur with packets from different VSATs, because all the time information is being broadcasted. So if this is not taken care, okay, then you can lose data. Abramson calls this method spread aloha and presents theoretical results which show that the method provides highest throughput for small earth stations. So by doing this, okay, by actually converting them in the form of packets and utilizing different time slots, okay, so they are able to have the highest throughput. Okay, so can someone tell me what's the throughput? You can unmute and respond. Okay, yeah. So we will get our maximum output based on all these type of protocols. And this is possible only by making use of the bandwidth in a much proper way, right? So this demand access, okay, technique, which is nothing but also referred to as a DAMA, okay, demand assigned multiple access, can be used with FDMA as well as TDMA. So So it's like a sandwich in between FDMA and the TDMA, which is compatible with both. But the only disadvantage is that the method is a reserved channel. So which means you cannot use that channel for something else. You have to reserve it for this purpose alone. Because whenever there's a demand that arises, so immediately it should be taken forward. So a reserve channel must be instituted through which the VSATs can make requests for channel allocation. So you have to make your reservations for the channels, and accordingly you can start your allocations. So VSAT systems operate in star configuration. I think in your network analysis you would have seen star mesh topologies. So the star configuration is what is followed by VSAT, which means that the connection of one VSAT to another must actually be made through the hub. Okay, so I will just check if I have that. Okay. So if you want to communicate with one VSAT, okay, to another, so it should be connected in a star, and hub should be able to communicate this information from one VSAT remote site to another VSAT. So directly they cannot communicate. They have to in turn send it to the hub, and from hub it connects to another uh, client. This requires a double hop circuit with a consequent increase in propagation delay, and twice the necessary satellite capacity is required compared with single hop circuit. So we need a double hop because it needs to communicate to the hub, and from hub it has to come back, right? So, so we need a double hop. And of course, when you have an extended circuit, then the power required, okay, and the, the the utilization of that double hop circuit also is much higher than your single hop circuit. In Hughes, a proposal is presented for VSAT system which provides for mesh connection. So sometimes we also go ahead with mesh, and that was employed with Hughes, where VSATs can connect with one another through satellite in a single hop. So instead of having the hub as an intermediate, so directly they communicate to the satellite, and from satellite it goes to the another VSAT client. But here what is happening, it needs to have a double hop, right? So what is the double hop? The first hop is it communicating to the satellite, okay, and then the hub recognizing the request, sending it, okay, and then it comes back to another unit. So here hub is actually increasing the number of hops. So instead what can be done is the request can directly go to the satellite, and from satellite it can recognize and send the information to the destined VSAT remote site. So in that way we are saving a single hop, which is extra due to this hub. Most VSAT system operate in the KU band, although there are some C band systems in existence. So most of them, okay, as I told you, they operate in a higher frequency range, which is KU band, even though, okay, we have some C band available. For fixed area coverage by satellite beam, the system performance is essentially independent of carrier frequency. So not only we are thinking of communication, but we are also thinking of performance. Okay, so performance should be of utmost importance because that's when we can rely on the system. If the performance is too low, then yes, ultimately we cannot rely on it, and we need to make sure that more parameters are considered. So this is essentially independent of the carrier frequency. For fixed area coverage, the beam width and hence the ratio lambda by d is a constant. Okay, so we are not only making sure that the beam width is being high, which means the coverage is high, but also the performance needs to be better. The satellite antenna gain is therefore a constant, and for a given high power amplifier, the satellite EIRP remains constant because the gain is constant, and ultimately the requirement, that is your EIRP, is also constant. If we have constant values, that is much better, okay, because we do not want any fluctuating values. So with fluctuating values, it becomes more dynamic and analysis becomes a little difficult. Okay. For a given size of antenna of Earth station and a fixed EIRP from the satellite, the received power at the Earth station is independent of frequency. So what's happening here? We see that uh, for a size of the antenna, the Earth station, and a fixed ARP from a satellite, the received power at Earth station is independent. So it is not dependent actually on what kind of size, okay, and what kind of EARP, is it constant or not constant, but your received power is actually going to be much more different. This ignores the propagation margins needed to combat atmospheric and rain attenuation. Now, as we all know, the major form of attenuation is actually with respect to um, uh, your atmosphere and rain, right? So, as the signals pass through, okay, you can experience a lot of loss because it passes through different layers, right? Okay. As shown in Hughes, which was in about 93, the necessary fade margins are not excessive for K-band, and the performance otherwise is comparable with the KU-band system. So VSATs, you know, comparing all this attenuation and the losses that can happen due to atmosphere and rain. Okay, so we need to combat these kind of margins. Okay, because ultimately we are concentrating on performance, so we need higher performance. So there are few negatives. Okay, some of the disadvantages of having a VSAT. Okay, so you can just take a note of them, and these are some of the major points to consider. So the first thing that you can observe here is that it has a high initial cost. Okay, so the initial setup is going to be very much high because you need to work on the satellite, you need to work on the hub, and then with the workstations, and then with the clients. So the cost is going to be tremendously high. So due to which sometimes most of them don't get into the concept of VSATs. Okay. Of course, it has its own advantages and disadvantages, but still, it becomes a expensive affair. The tendency towards optimizing systems for large networks is typically we need about more than 500 VSATs. Okay, so if we want a larger network, then we'll have to look for VSATs which is more than about 500. So lack of direct VSAT to VSAT link. So as I told you, a VSAT cannot communicate directly to a VSAT, but then it needs to communicate via a satellite. So which means if you have just set up these client machines, okay, if you have set up these machines and say, for example, even if you have a host computer and a hub equipment, but if you do not have a satellite, if there is no satellite, then these things will not work. So even if I want communication from one VSAT to another, that is also not possible. So say, for example, the first VSAT wants to communicate with the third one, okay, and it seems to be easy, but then it happens only with the help of satellite. Okay, so signals have to pass from here, from the first one to the satellite, and from the satellite it needs to come down if it's a single hop. If it's a double hop, then it comes to the hub, and from the hub the information goes to your outdoor unit, so that becomes a two hop. Okay, so that's one of the major disadvantage of a VSAT. So there are a lot of technological equipments, okay, and improvements also with regards to VSATs. Okay, not like those from the days that it was launched. There can be a lot of improvements. There can be a lot of software upgrades that can happen with regards to these satellites. So it can be in the area of microwave technology, DSP, and this will result in VSAT systems in which most, if not all, of these shortcomings will be overcome. So there is going to be a lot of developments, okay, in the field of DSP, in the field of microwave, because that's how your signals are processed. So, so if your signals are being able to process in a much better way, then these shortcomings that we saw initially, right, and lack of communication between each VSATs, and optimizing a huge network, and the cost will all come down. Okay, so the next concept that we will be actually looking into is Radarsat. Okay. So Radarsat is an Earth resource remote sensing satellite, which is part of the Canadian space program. So each country will have its own program, and this is basically concentrating on remote sensing. Okay. So it can be the underwater table, underground water levels. It can be the uh, forestation, deforestation information, and the type of vegetation. Okay, it can be with regards to weather. So radar sat 1 was launched in 95, and the second version, or the second satellite, was launched in 2006. See, you will need at least 10 years to work on a satellite and to make it more refined and launch it into the space, because we cannot send in a half baked information to the space, right? We need to have a fully functional um, device which actually works in the space. So some of the objectives of this radar sat are, okay, you can just make a note of this. So these are some of the important points that you can uh, think of when you are uh, discussing about radar sat. So it provides application benefits for resource management and maritime safety. So not only with regards to information, but also with regards to management. So it helps in managing things well, because we have information, and information, with information you can actually uh, decide as to what is going to happen. Develop, launch, and operate an Earth observation satellite with synthetic aperture radar. So SAR. Okay, it's not specific absorption rate, but then it's synthetic aperture radar. So we can develop, we can launch, and we can also operate the Earth observation satellite. So this establishes Canadian Mission Control Facility. So this is as good as your TTNC, okay, telemetry tracking and control. Market radar sat data globally through a commercial distributor. So we can not only design, but we can also market them through to the whole worldwide through a commercial distributor. So you will have to recognize a distributor, and once your radar sat is fine, okay, then you can start commercializing it with the help of a distributor who has global contacts. make SAR data available for research. So what is this SAR? Synthetic aperture radar. So whatever data that has been collected from your radar that can be actually given for the purpose of research. I don't know how many of you are aware of the latest information that there were few samples which was taken from the Japanese satellite, and those samples are now being tested. Okay, and various analysis can be done. So satellites actually play a very major role in exploring the outer world. So it maps the whole world with a stereo radar. So mapping is possible. In fact, if you can look up for information, they are trying to map the whole space. Okay, wherein like how you have maps individually for each country, for each continent, streetwise. So they want to create maps even for the space. Okay, so that's a huge task, but then it requires a lot of data, a lot of information, a lot of analysis uh, on the positions of these outer bodies. So this can map Antarctica in 2 seasons. Fine. So the applications so far that we have seen is, as I told you, with iceberg detection, oil pollution, ocean feature mapping. Is it very much necessary for this ocean feature mapping? What importance does it play? Yes, ocean mapping, is it so important? Is there any major impact if the water bodies are disturbed? Yes, can someone unmute and respond? Soumya, Raghav, Shreyas, Jitendra.
Yes, sir.
Yeah, is it important for the water bodies to be mapped? Or can someone give in some information on this question asked? Now, depending on the type of color, okay, of the soil, we can actually know it is rich in iron or is it rich in something else, right? Similarly, when we map the oceans, okay, we can find out if it's fine, if it's doing good, or is there a lot of pollution, or is the level of ocean increasing, decreasing? What could happen to the neighboring countries, or what could happen to those regions which are just across the ocean? So all this information is life-saving, critical, either for humans or for those aquatic bodies. Then oil pollution monitoring. Many of the factories, they uh, they just leave out uh, their pollutants, okay, into the water body. So due to which the aquatic animals would suffer. So Radarsat helps in actually monitoring as to what is the level of pollution in a specific area. Then ice mapping can also be done so that you can decide your route while you're on ship. And then your iceberg detection, very much necessary so that it protects your ship against wreckage. Then crop monitoring. Okay, so with the help of weather, um, regular updates can be sent to the farmers, and they can be advised on what crop would be suiting for the upcoming seasons, for the upcoming months. Then forest management. Okay, how much of area is actually forested, and is there any deforestation happening? Is there any land acquisition happening? Okay, so all that can be actually checked with the help of Radarsat. Then land use mapping, how much of land is utilized, or is any forest destroyed and they are they are occupied. Geological mapping, topographic mapping. So n number of applications that can be thought of when we study about radar sat. Okay, so just a few information about radar sat is that they are planned to fly in LEO, low Earth orbit. Okay, and some of the details that you can look into is that it flies at an altitude of about 800 kilometers, and the inclination is 98.5 degrees, and its period, okay, its period is about 100 minutes. Okay, 100 minutes, and it takes about 24 days to repeat. Okay, so which means it comes back to its original state. So these are some of the information with regards to radar sat. So in our upcoming classes we will see few more features, and we will see as to how the transition happens, and few more configurations we will just look into when we discuss about radar sat.